Ladies and gentlemen, we are now pleased to introduce our first panel of the day, entitled The AI Takeoff for Robotics. Moderating this discussion will be Abby Kukura, Director for Future Technology Platforms at the Special Competitive Studies Project. Please welcome our panelists. Dr. Steve Chien, JPL Fellow, Senior Research Scientist and Technical Group Supervisor of the Artificial Intelligence Group and the Mission Planning and Execution Section of the Jet Propulsion Laboratory. Rev Lebaredian, Vice President of Omniverse and Simulation Technology at NVIDIA, and Damion Shelton, President of Agility Robotics.
Good morning, everyone. I'm so pleased to have with me today perspectives from different parts of the tech stack for AI and robotics. Rev from NVIDIA represents the software layer, the operating system for robotics and AI to converge. Damion is the agility guy that Mark was referring to, is building a robotics company, with Agility Robotics, a bipedal humanoid robot. And Steve Chien, with his work at NASA JPL, is representing one of the most compelling use cases for AI and robotics. So I'd like to start by asking each of our panelists today, what is exciting you the most about AI and robotics today? How have things changed in the past few years, and what excites you about this field? I'll start with Rev.
The biggest change for robotics in the past few years is generative AI. In the decades leading up to this, we've had the promise of robotics being just around the corner. We probably had the fundamental technologies to build the physical aspects of a robot and build good ones for a long time, but we really didn't have a line of sight to building a good robot brain to make it useful. It wasn't until a few years ago that we realized we finally have the fundamental technologies. What we saw with ChatGPT a few years ago convinced the world that we now have crossed over this threshold into a new kind of intelligence that could be general enough to power a robot and make a robot brain that's actually useful. So now you're seeing everything you just saw in the previous presentation. I think is indicative of what's happening. We're going to see an acceleration of the development of robots, and particularly humanoid robots, because we finally unlocked the last piece, the technology necessary to create a robot brain.
Damion, what are you seeing from the hardware perspective on this?
Yeah, so there's been a lot of changes in just the last, call it 10 to 15 years on the actuator side. So for the non-roboticists, actuators are the things that make things move on a robot. And the power density and the force transparency of those have gone up dramatically in the last 10 years. Interestingly, there's a high level of adjacency for those of you who are bicyclists. The e-bike market has really helped to depress the cost of both compact batteries and these high torque motors. But I would agree on the software side, when we were first fundraising for the company about 10 years ago, the investor was asking me to explain, so how are you going to program these robots? And I said something like, well, we can just have an engineer write an application. He's like, well, how many applications do you think there are for robots? I was like, well, 1,000, 10,000. So he's like, so explain to me how you're going to take this check that I'm writing you and hire 1,000 programmers to develop applications for the robot. And that gets back to the work we're doing with NVIDIA and others on having a modular set of pieces out of which applications can be constructed, but using generative AI to piece those things together. And that's one of the most exciting things just from the last couple of years that's really started to answer that question for us, which was an open item for a long time, which is, okay, robots are great, but doing things with robots is ultimately more important. How are we going to go about doing that?
And Steve, your thoughts?
So to me, the most interesting developments in AI and space and robotics are first that we finally have uptake on a lot of large missions. So the rovers that we have on Mars right now have significant artificial intelligence on them that helps them select science targets, drive over more challenging terrain, and to accomplish more science with the same amount of resources. And more recently, we've seen an unbelievable explosion in the amount of AI that's in Earth orbit. And this is the kind of space that really affects the everyday lives of people. When they take out their cell phone and it gives them driving instructions, they're relying on space. Now, if you have a very recent cell phone, you're You can actually talk directly to space assets using text messages. And the applications of artificial intelligence there are truly amazing in terms of the ability to monitor natural hazards, such as the hurricanes that we just had in the southeast United States, volcanic eruptions, air traffic all around the world. These are going to be changing the way that we interact with the Earth's environment.
Thank you. Rev, I'd like to go back to you. You've had a really fascinating career. It started in the entertainment industry, and you've been at NVIDIA for over 20 years, spending a lot of time working on simulation environments for video games. And now that the world has woken up to AI and we're building the robot brain, how does this work you've been doing in the past few decades, what's the through line from Hollywood to video games to robotics?
In order for us to create the AI that are the fundamental components for creating a robot brain, AIs that can perceive and understand the world around us, AIs that can understand the laws of physics well enough so that you can actuate, like Damion was talking about, in the world and do useful things. We need to train these AIs in an environment that matches the real world as closely as possible. And so the best way to do that is to do that in simulation, to do it in simulators that match the real world closely so that we can safely train them in diverse environments and have them learn about the world and the physics of the world without endangering us as they're learning out here. My background in entertainment comes from visual effects for computer graphics for movies before I joined NVIDIA. And then I applied those technologies to building video games, which is fundamentally the same technologies but done a lot faster so we can interact with it. What we realized years ago when this whole AI thing started back over a decade ago was that the most valuable AIs we're going to create are going to be ones that operate in the physical world around us, and that we're going to need to create some way of creating all of the data to train these AIs, and that's probably going to come mostly from simulation. So we adapted the technologies we built for simulating worlds for entertainment purposes, for video games, to simulating the real world as closely as possible. And that took us on this journey we're on right now to create what we're calling the Omniverse operating system for building and simulating virtual worlds for the purpose of building things in the real world and primarily for building AIs in the world.
Damion, I'd like to ask you a bit about how AI has impacted Agility's tech roadmap. So are there any particular advances? There's the foundation model, there's transformer models. Is it the transformer model that has changed the tech roadmap? Is it advances in the post-training stage? What are the specific advances in AI that have impacted how you're doing your work?
Sure, so I'll actually have some video on this afternoon as part of the demo session. But yeah, I mean, if you look sort of back 10 years ago, so first off, all of us in the robotics industry know each other. So my co-founder at Agility had actually had Al Rizzi, who worked with Mark Rabert at Boston Dynamics years ago. So there was an extremely physics-oriented approach to robotics circa 10 to 15 years ago. That has, and I mean literally in the sense of write down math equations around how the world works, and that ultimately is your robot control. As I said, one of the things that we're experiencing now is that you can take those individual pieces and have sort of an answer to a problem comprised out of a natural language description. One of the most surprising things that we've done in the last 2 years, in a very surprising 2-year period, is being able to hook at a very high level large language models onto an existing control stack and have useful stuff come out. And I would say for those of you who think that it might be obvious that that works, it is not obvious to roboticists that that would work. And literally you can just teach LLMs the API, the programming interface for the robot, and say, okay, I need you to move a piece of trash into a bin, please do that. And because the robot knows how to pick things up, because it knows how to walk, it has no idea, the robot has no idea that a bin exists or that trash exists, but nonetheless, you can complete tasks. And that is extremely new. I would say that was a nearly unsolved challenge in robotics for the entire history of the field. And very suddenly now you can just get cloud compute services for 5 cents an hour that will solve that problem for you. And it's such a profound change that it's difficult to explain how much that's impacted the industry.
Steve, can you explain why space is the killer use case for AI and robotics?
Yeah, so the way that most space missions are operated is from the ground, they figure out what they're going to look at, and then they program the satellite to do that. And there's different levels of automation so that you can be better and more efficient at doing this. But Jan LeCun famously said that LLMs are no smarter than a house cat. And my comment is that we wish that our spacecraft were as smart as a house cat, because all they do now is they take all this imagery and we sort it out on the ground. But even the dumbest house cat, or I even would say the dumbest rat, knows how to hunt for food. It smells and it goes and looks at it and it goes and stays where the food is. This is our goal, to make the spacecraft that smart. So we have mission concepts under development where we use different instrumentation from other satellites or on the same satellite to go and look at the most plausible locations where there are these rare weather events like deep convective ice storms or wind shear events, because getting data on these, and some of these events may only last tens of seconds or a short number of minutes. And we want to get data on these events to help drive our understanding of the Earth's atmosphere and climate. And these measurements can only be made by staring at these phenomenology at the rare times that they occur. If you just take video of all of the Earth, the spatial and temporal resolution that you have will not enable you to understand these complex events. And then we'd like to scale that to what my dream is, which is to hunt for life beyond Earth. And we're working on an editorial for this right now with astrobiologists. If we discover life beyond Earth, it has to be with an AI-powered robot, because the ability to send humans to Europa, to Enceladus, the places where this life is likely to exist, is not within our reach, within our budget, within our technology right now. We need to go and send these robots there. They need to be in situ, in the ice, sampling and hunting for these astrobiology signatures so we can answer these questions like, are we alone in the universe?
Thank you. Damion, I'd like to go back to you and ask about what the remaining technical challenges are that we need to solve for robotics. What are the unsolved technical challenges that we still haven't quite gotten right, but that will unlock progress in the field?
Yeah, there's a couple of them. One is right now, although agility has probably the most cost-effective human-scale humanoid robot on the market, cost is one of them. Fortunately, that is generally solvable with sort of the march of technology. Just in the last decade, humanoids were not an available product, and so the fact that they exist at all is an important step. So I think that's solvable. That's not one that I would throw on my list of the to-do list for the immediate short term. Safety is probably right now the largest single barrier to commercial deployment. With some of the videos that I'll show this afternoon, we've been focusing on very constrained warehouse tasks, and that allows you to process control the safety problem. Basically close a room off, say robots and trained people are allowed into this room, civilians are not allowed into this room. You can solve the safety problem that way. And there's a lot in the logistics space where that is actually a totally reasonable approach. There are a lot of unsafe things in warehouses, and you train the people to operate around them. But that does not unlock, say, the next 99% of the field. So having robots that have a high degree awareness of people in the environment, and in particular ways to operate safely around people, because the example we always give is there's nothing inherently unsafe about a humanoid robot. It's about the size and weight of a person. On the other hand, if I have a few too many drinks after this event and get a little unstable, me falling into you is going to do the same amount of physical damage as a robot falling into you. Generally, though, with people, right, we have self-control. We don't have those kinds of problems. When you start hooking AI systems into robots, it gets a little less deterministic from a control standpoint. So the example of how we think about the presence of these robots in our environment, and in particular, when they're applying forces to the world that are about human scale, is probably the biggest single thing that we're thinking about here. We have made some hires. Melanie Wise on our team, who was formerly at Fetch Robotics, is the world expert on how to deploy autonomous systems safely. She's done it with AGVs, autonomous ground vehicles, in warehouses, and is now working on that with us with humanoids. So that's the big thing that I'd love to see the field answer questions for, is how do we have things around us that are the size and performance of people that we feel safe around, and where there is a good safety track record, because that was a problem with the early history of autonomous cars, and humanoid robots will see it next.
Rev, can you talk a little bit about the role of simulation environments in helping to solve that problem that Damion laid out?
We need simulation environments for two reasons. First is to create the AI, create the brain to begin with. We need a sandbox or a safe space to build the robot brain, and we need to do it very quickly in diverse environments. So simulation helps us there first. But once you have a brain that you want to go deploy into a real physical robot, before we actually unleash it into the world, given what Damion was just saying, we'd like to make sure that it's a good robot brain and it's going to do the right things. The first robots we're deploying into the world at scale are self-driving cars. We'd like to have the brains of those robots tested in a virtual world driving millions of miles before we put them out into the world. Anytime we make an update to that software, you want to make sure that it's going to work before you deploy it. And so simulation serves us in both of these cases, in order to construct the brain to begin with, and then to ensure that it's a good brain before we unleash it into the world.
Steve, you have had roles in various parts of the ecosystem. You served on the National Security Commission for Artificial Intelligence. You have a hat you wear at Caltech, and you are working for NASA JPL, which is a government agency. Looking across these different actors, where do you see untapped potential in the innovation ecosystem for robotics? Where are there resources, latent resources or potential that we should be leveraging to drive this technology forward?
Well, that's quite a challenging question there. So in the space arena, which is probably where I should confine my remarks, there's multiple parties in the ecosystem. There's, the traditional players like NASA and JPL, the national players. There's large companies, and then there's the new space arena. And I would say that all of those working together is the challenge to sort of crack the nut, because they all bring different things to the table. And then there's also various problems, such as, how do you send a spacecraft to Europa versus how do you just get a bunch of reasonable cost satellites in a low Earth orbit? And the different players in that field bring different skills. And I can tell you, just in my team, we're partnering with about a dozen new space companies, and the speed with which they can work and the cost with which they can work is something that we really need to harness in the space industry in order to be moving forward, because the challenge always in the space industry is cost. It used to be, okay, to do anything, it was a few $100 million. That cost is ridiculously low now. You can have a 150 kilogram satellite that's reasonably capable in orbit for about $8 million, which might sound like a lot of money to people, but that's nothing compared to what it was 10 years ago.
Rev, when people think about NVIDIA today, they think about compute and GPUs. What are the computing needs of different parts of the robotics stack? There's the robot brain, there's the simulation environment. What are the compute needs of these various components of this ecosystem?
Yeah, most people, when they think about compute for robotics, think about the computer that's in the robot, which makes sense. That's a very important computer. It's the one inside your self-driving car, or the one inside your humanoid that's powering the brain of the robot. But before you can get to that computer, before you get to that robot, you have to actually construct the brain. To build that brain, you need a different computer. And that's what we are calling the AI factories. That's what NVIDIA is busy building right now, and all of the data centers with the AI supercomputers being built are essentially this AI computer where we feed a bunch of data and power into it, and out comes intelligence that we can then deploy into the field. But the less understood computer is the simulation computer. In order to train an AI, it needs to be fed with a lot of data information about the world. And that information is going to come from primarily simulation. It's going to be a combination of real world data, but a lot of data from simulation. And then we need to test these brains. So there's three computers essentially: the AI computer, the simulation computer, and then finally the actual computer that powers the brain of the robot. And we're building all three.
Damion, could you talk a little bit about data and how data plays into Agility's work?
Yeah, so we actually are very definitely in camp simulation in terms of how we've approached some of the training on the robot that's not otherwise physics determinate. And the reason for that is that what you want to see in training sets is dangerous, surprising things. And if you rely on the physical world to see dangerous, surprising things, you're either going to wait a long time or you're going to have a very unwise training program. So what we use the simulation environment for is to expose very large populations of robots to novel environments in a way that would be totally impractical to do even with VC money behind you. What we've seen with this is that it allows us to decompose this into a couple of problems. There's the cognitive piece of the problem, which we, at this point, largely can rely on, for lack of a better word, commodity LLMs, as weird as it is to think about that kind of thing as a commodity, and then the physics side. And the physics side is frankly the more challenging of the two because interesting things happen at millisecond timescales with robots physically that don't happen cognitively. If I just stare off into space for 5 seconds, it's not as much of a problem as if my heart stops beating or if I fall over because my muscles stop contracting. So when you think about the control problem for robots, one of the things that simulations offer is the ability to explore these very detailed timescales that you would not get via teleoperation or would be statistically very unlikely to occur with physical training sets.
And Steve, how is AI changing the process of scientific discovery in space?
That's a great question. So right now, as I said, the missions collect all the data and then we kind of bring it to the ground and the science teams figure out how to make sense of it. In the future, we're going to see a much more collaborative venture where the scientists actually need to define the policies, and by this I mean the computer science policies, not the political policies, the policies by which the spacecraft operate. So under what circumstances does that look enough like a deep convective ice storm that I'm going to devote my I'm going to focus my satellite assets on that. And we're already seeing that. We've been operating what we call the Earth sensor web for about almost 2 decades now. And this marshals together a lot of Earth observing assets. And when we get news or satellite notifications or ground notifications that a volcano is erupting or an area is flooding, we allocate satellite resources to observe that. And the very interesting thing in this is that the science team had to figure out what are the policies, what are the priorities, where before it was more ad hoc of, oh my God, we've seen this happen. I call up one of my buddies and we try and get a satellite to take some imagery of that. Now we have to think much more deliberately about these kinds of priorities, and there is nothing more explicit than some software policy.
So I'd like to close with a rapid fire question to each of our panelists about a tech moonshot. So something SCSP likes to do in our work is think about what is the moonshot or the technical ambition, the national ambition that would create a position of advantage in a technology that we want the US to lead the world in. So I'd like to ask each of you, what is your moonshot for AI and robotics that would create a position of advantage? And what are the key things we would need to do to get there? I'll start with Rev.
Applying AI to the physical world, I think, is the most important thing we can do with this new technology that has arrived. And that's essentially robotics. We need to bring robots out here into the physical world to help us build all of the things we need to build and build the world around us. That's a pretty big question. What would we ask the US government to go do as a moonshot to drive this? I think if we could find some project to rally around to create a fully lights out factory and supply chain for some supply chain for something that's important to the US, that would drive a lot of innovation and creation of technologies and standards necessary for this thing to flourish. In order for us to build such a thing, we not only need to build the physical part, but we need to build the digital twin, the digital representation of the factory with all of the automation of the supply chain, the whole network. And that's going to require a whole host of technologies, tools, protocols, data formats, and standards. And if you think back to one of the most profound things the US moonshots have produced, it's the internet. In the early internet, all of the standards that we rely on were constructed, that came out of this thing, stuff that most of us don't ever think about with the basic protocols. We need that for digital twins, a representation of the world inside the computer.
And a goal like a lights out factory would help get us there.
Yes.
Yeah. Damion, over to you. What's your moonshot?
Yeah, I would love to see the US invest in the whole back-end infrastructure for robotics because we are in the early enough phase of this from a rollout that we don't have the supply chain, say, that exists, say, on the automotive side of the universe, or solar panels or other big sort of national or international scale projects. I think the US has the opportunity to build that out. Certainly most of the technical expertise is in the US right now. And that's one of the reasons why Agility has been manufacturing our robots domestically out of Oregon since the beginning of our company. But I would say from a broader moonshot perspective, in addition to that, I would think the thing that we'd love to see is more of a national recognition that robots can be partners for people in job roles. One of my favorite examples, we have Amazon as an investor, and we were at an event with them last year, and the stat that they shared at the time was that the Kiva robots, so if you go on Google and search for Kiva robot, it's the autonomous shelf-moving robots that Amazon uses. When they acquired Kiva about 12 years ago, there were 0 Kiva robots deployed, and they had about 60,000 human workers at Amazon. In the intervening decade, or decade and change, they deployed 750,000 Kiva robots. So you might say, well, oh my God, clearly they didn't hire anybody. Their human workforce went from 60,000 to 1.2 million in the same time. So I think the US right now has the opportunity to view robots as a partner for economic expansion, and in particular, a partner that can take some of the wear and tear off of human bodies. And I would love that to be one of the focuses, is say, like, look, this is not an either or situation moving forwards at a national level scale. We have the opportunity for our technology to actually enable humans both to increase economic output and reduce the physical damage that these kinds of jobs have on people.
And Steve, let's close it out with you. What's your moonshot?
Yeah, so I kind of teased this before. The moonshot that I would propose is use AI and robotics to go answer the question, are we alone in the universe? So Europa and Enceladus are the 2 locations in our solar system where we could go and send robots to see if there is life there, or signs of life or prior life. Europa is one of the moons of Jupiter. Enceladus is one of the moons of Saturn. We can't send people there. If you send a robot, for example, to Europa, it's only going to last about 30 days on the surface, and you can only talk to it less than half of that time. So it's pretty much got to be autonomous. It has to. We've used AI to make space robots do things better, like the Mars rovers. We haven't yet asked them to conduct judgments. And really, those entities at Europa and Enceladus have to exercise judgment and balance risk and reward, because it has to ask questions like, what is the sampling site that looks the best? If I start sampling and it takes too long, do I switch to another sampling site? How well do I know that my batteries are going to last? Are they going to run out before I can communicate my results back, in which case it doesn't matter if I found life? Or is it worth it to go ahead and sample there and use that energy because I think that I'm going to find life there, and then I can communicate that back? And if you're not a philosopher and finding life isn't enough, I'll give you another moonshot, which is saving your own skin. We have near-Earth objects, and if the wrong near-Earth object hits the Earth, it's a bad day for all of humanity. And one of the concepts to go and study the near-Earth objects the best for planetary defense is to send 100 fire-and-forget spacecraft to go and explore them and come back to the Earth. And the reason why these have to be fire-and-forget is, A, nobody can pay to operate 100 spacecraft, and 2, in order to get 100 spacecraft at a reasonable price, they have to be so small they can't even communicate until they come back to Earth. So they have to conduct their mission autonomously and answer questions about, are these asteroids more like the asteroids in the main belt, in which case they're very dangerous, or are they more like comets, in which case they're very fluffy and not dense, and they're not a threat to humanity.
Well, there we have it. This was a wonderful conversation with the three of you. These are some great goals that we can think about during the rest of today's conversations. Please join me in thanking our panelists.